So, good evening, everyone. So this is the sixth class of one, two, three, four, five, sixth class of stochastic processes. Uh, Stochastic processes. Um, Sixth class. So first, what I'll do is I'll give a recap on what I did in last class. So in recap, we started studying first the Poisson process, the motivation for Poisson process, and why Poisson process is basically needed. So in the motivation, we saw that whenever you have some random process where you want to count some number of events happening in a certain interval of time, then you use a Poisson process to model it. So for example, if you want to count the number of cars that have passed through a road, then you can model the number of cars that have passed the road as a Poisson process. So last time we gave two definitions of Poisson process. So there was first definition. So for the Poisson process, you wrote it down as a collection of number of events that has happened at time t. The nt is a random variable. You have set of nt's for all t greater than or equal to 0. This is a Poisson process if 1 n0 equal to 0. So at 0 time, there is no event has occurred. 2, if it has independent increments. So last class I gave an example of what you mean by independent increments. So if you have a time scale on which some random process occurring, and you see that this is one time interval and this is one time interval. If these two time intervals are non-overlapping, then the event that has happened here is independent of the event that has happened here. That is the meaning of independent increments. So when you say that you model the number of cars that pass through a road as a Poisson process, that is not the true real life model, because there could be cases that, okay, suppose an accident has happened here in this interval, then it will affect the number of cars that pass through this road at this interval. That is the real time situation. But real time situation modeling is very difficult. So you use some assumptions to model those in your real life. So one of the assumptions that makes the math easier is you assume that whatever happens in this interval does not affect my random process which happens in that interval. So this is the first interpretation of process. Next, when we go into Markov process, you'll see that there is a dependence on the past. So that's why I first started with Poisson process, and then I went to uh, I'll go to Markov chains, because in Markov chains you'll see that the independence thing is not there. So the first motivation for the Poisson process was independent increments. So at each non-overlapping interval, the random process are independent. And the third one is number of events in any interval t is Poisson distributed. So hence the name Poisson distribution. The mean is given by lambda t with the parameter lambda t. So what that means is probability that n t plus s minus ns equal to n equal to e power minus lambda t into n by n factorial. From this, you can see that this is a Poisson distribution. So what this means is, again, you have the number line t. And what this is saying is, okay, let this be t plus s and let this be s. So NTS, this is number of events happening NT, this NT plus s. And this is NS. So NT plus s minus NS gives you the number of events that has happened in this interval. So the number of events that have happened in that interval depends on the length of the interval, nothing else. The length of the interval is t. It doesn't depend on various short variable. So this is like the third statement is equals that it's stationary. So it does not depend on where you start and where you end. It depends on the difference of where you have started and where you have ended. So these kind of properties is inherently gives you that the Poisson process has stationary increments, and you get the distribution which is Poisson distribution. Okay. So if you have a process, if you have a process which follows these three, then we call them as Poisson process. Okay. I hope that is clear. Um, okay. Next, I'll give a definition of something else which we'll use to define Poisson process last class. So what I'm saying is let f be a function. F is said to be small o of delta t if limit delta t tends to 0, f of delta t by delta t equal to 0. So this is the notion of um, small o of h kind of stuff. We saw this in last class because we use this to define Poisson distributions again. So what our main motive was to find the probability of one event occurring in a small delta t neighborhood was given, and then more than one events occurring in a small neighborhood was also given, and using those we got back the Poisson distribution, the number of um, events that the probability that number of events occurred in a interval t is equal to n was Poisson distributed. We got it from the definition 2. So definition 2 was again Poisson process you denote by the counting process. So the counting process is a random variable where you have number of times some event has occurred. Is Poisson process with rate lambda greater than or equal to 0. If 1 n0 equal to 0, that remains the same. 2 process have independent and stationary increment. 3 probability that n delta t is equal to 1 is lambda into delta t plus small o of delta t, small order of delta t. So as you can see, as delta t goes to 0, this goes to 0. 4 probability of n into delta t greater than or equal to 2 is equal to small order of delta t. So as delta t goes to 0, the probability that more than two events happen at the same instant goes to 0. Same with like if you want to model something like number of cars passing through a road, or number of buses, like simultaneously both can't happen. In reality, that is not true. Where if you have a bigger road, then two cars can pass simultaneously through you. But for the math to make sense, we first dump it down so that it is easier to do the math, and then we collect the real values. Okay. So last class we defined the Poisson process. We gave the two definitions of Poisson process, and we showed how does definition 1 imply definition 2 and definition 2 imply definition 1. We also gave uh, uh, we also gave an okay, maybe I'll show that. Yeah. In Poisson process, we gave the motivation behind Poisson process, where we wanted to count the number of cars that have passed in an hour. So we started by the most basic thing of using binomial distribution. We used the binomial distribution, and we thought that okay, maybe binomial distribution would give us a good model of uh, the number of cars that have passed through. But then we saw that two per cars can pass in a minute. Then what happens? So what if multiple cars pass in a second? So what happens? So you try to decrease the intervals that you have defined when you have modeled it as a binomial distribution. And as you decrease the intervals, you see that finally what you get is a Poisson distribution, the Poisson distribution. The Poisson distribution pops up from the binomial distribution. While modeling something on the continuous scale, where you have a continuous time scale and you want to model uh, mm, the number of times an event has occurred in the continuous time, you use Poisson distribution. So yeah, this was the recap on the last class. So in the last class also I mentioned that there are actually two ways of looking at Poisson process. One is you keep a track of how many number of events has happened till the time t. That is one way. The other way of looking at is uh, what is the time that the next event will happen. That is also random. So you can also model it as uh, the inter-arrival times, what we call as the inter-arrival times or the waiting times. The waiting times, the total waiting times, inter-arrival times. Okay, so I'll go one by one. So we have inter-arrival times and waiting time distributions. So let me consider xi is the x1 is the time of occurrence of first event. So time of occurrence of first event is x1. You know this is random because you don't know when the event is going to occur, but at some point the first event will occur. Xn is the time between n minus first event and nth event.
போட்டு இருக்கு iOS press தான் வந்து ஸ்கோபஸ்லயுமே இருக்கு.
Hello, could you? Thanks. So x1 is equal to time of occurrence of the first event. Xn is equal to time between the n minus first event and nth event. So now here events could be anything like it could be when a car has arrived, or if you have a machinery setup, when the failure will occur, or when will there be damage in that, or if you are worried about accidents that occur throughout a year, when is the accident occurring, or if you want to model natural disasters, those. So all of this. So event could be anything. It is a point on the time scale, just when it has happened. Okay. So now again you have the timeline. Okay, and what these x1s and xn's refer to is, so suppose an event has occurred here, another event has occurred here. The next event occurred just immediately after it, but then it took some time. So these are random events which have occurred throughout the time. So what I call it x1 is the first event occurrence. X2 is the time that between second and first event occurrence. This is x3 and so on. So now what we are interested in, could we characterize? So if we know the Poisson process, could we find the distribution of the inter-arrival times, the times between the two arrivals? So can I try to find the distribution of xn? To find the distribution of xn, we'll use the definition of Poisson process that we know, that nt is a Poisson process and nz equal to 0, independent increments, stationary increments, those both, and the number of events that occur in an interval t is Poisson distributed. So we'll basically mostly use the definition one because that is easy to use. So first for finding the distribution of xn, we'll first find the distribution of x1. So the distribution of x1, I want to find probability of x1 greater than xt. I know you basically want to find x1 less than or equal to t, but instead of finding x1 less than or equal to t, I'll find the CCDF, the complementary function, probability of x1 greater than t. This is given by probability of this is equal to nt equal to 0. So x1 is greater than t. What does it imply? So this implies that the first event has occurred after time t. So what does it mean? That till time t, no event has occurred. So the number of events that has occurred till time t is 0. So I hope you see the similarity between these two events. So x1 greater than t is just saying that no events have occurred in the time interval t. And the Poisson distribution for 0 is e power minus lambda t. The CC, this is the CCDF. So from here we can say that x1 has exponential distribution with mean with the parameter one lambda, 1 by lambda, with mean 1 by lambda and with parameter lambda. So for x1 we know that uh, the distribution is exponential. Next we want to find the distribution for probability of x2 greater than t. So, but before finding the probability for x2 greater than t, what we'll do is I'll write probability of x2 greater than t as probability of x2 greater than t given x1 equal to s. So why does this make sense? Okay, so we can write this as x2 greater than t and x1 equal to s by probability of x1 equal to s. Now, you see x1 and x2 are two non-overlapping intervals of time, because x1 is the time till the first event has occurred, x2 is after the first event has occurred till the second event has occurred. So they both are non-overlapping, hence independent from the definition of Poisson process, independent increments. So these both are independent. I can write the joint distribution as a product. This cancels out. So conditioning just give, so since you can also simply say that since x2 and x1 are independent, conditioning on x1 is simply the event x2 greater than t. So it is sufficient to find this uh, uh, the probability of this event, a conditioned event, that gives me the probability of the event that I'm after. Okay, so now the probability of this event is probability that 0 events have occurred in s comma s plus t given x1 is equal to s. So what is this saying? So again, you have a timeline and you say that, okay, at s, at time s, x1 has occurred. This is x1. Now you are saying x2 should be greater than t. x2 being greater than t, so let this be s plus t. Then x2 should be greater than this is the intermediate thing we are seeing as t. So between s and s plus t, nothing should have occurred. If something has occurred here, then x2 is less than t. So x2 occurs after s plus t. So 0 events have occurred in s comma s plus t given x1 is equal to s. Again, using the intermediate increment property, we get probability of 0 events in s to s plus t. This is again e power minus lambda t. Therefore, x2 is also exponential. Similarly, doing induction on all of these, you get that all x's are exponential. Okay, so intuitively, what this means is since you have a process which has independent increment and stationary increments, it is equivalent to say that after each event, the process just restarts itself. So after each event has occurred, it again waits for exponential time and another event occurs. Again, one event occurs, it forgets what has happened before, it waits for another exponential time and another event occurs. So it is independent and also the same, and stationary means the distribution is same as it was for the first event to occur. So in other words, what happens is the process that you have modeled using this Poisson, it has no memory. Since it has no memory, it is obvious that the inter-arrival times would be exponential. Like that is the intuitive way of thinking. But you also have the math backing it up that if you have a Poisson distributed uh, process, then the inter-arrival times between the events are exponential. Okay, so These are the inter-arrival times. Then there is something known as the waiting times. So waiting times are basically Sn is the arrival time of nth event when the nth event has occurred. So this you can see that Sn equal to summation I equal to 1 to n xi, n greater than or equal to 1. So yeah, mm, what this means on the time axis scale is, so suppose this is my time, these are the events, and some events occur randomly. So xi's are, this is x1, this is x2, this is x3, and so on. The waiting times are, this is s1, this is s2. So how, once the process started, how much time you had to wait till second event has occurred, that is the s2. And then you have s3. So as you can see, S2 is basically the sum of x1 and x2. S3 is basically sum of x1, x2, x3. So you add up inter-arrival times, you get the um, nth event arrival time, nth event waiting time. Okay. So one very important observation here. Uh, so this many people will say that it's trivial. It is trivial, but it takes some time to understand this notion. So the event nt greater than or n equal to the event Sn less than or equal to t. These two things will be using left and right to interchange Sn and n. So yeah, you saw here how I try to relate the events x and n's. Similarly, in most of the Poisson distribution problems, Poisson process problems, we'll try to interchange between nt and snt. Once you have snt, you can change it to xnt. So growing from nt to xn, you go from nt to sn, and then from sn to xn. I'll draw a small map saying short this way how to characterize a Poisson process, that I'll come. But first I'll say why these two are equivalent. If it is obvious, then it's good, but I'll just state it. So what does nt greater than n equal to mean? Nt greater than n equal to means that um, so this event means that uh, number of events till time t is more than n. So more than n events have occurred till time t. So what can I say about nth event? When did the nth event occur? Nth event occurred before or at t. So if nt equal to n, then nth event has occurred. You can't say if nt equal to n means n events have occurred till uh, t. But what nt greater than equal to n means that nth event has occurred either before the time t or at time t. So what this means is Sn, the time Sn is the arrival time of the nth event. The arrival time of the nth event less than or equal to t. So one way implication you have seen. So nt greater than n implies Sn is less than t. The other way implication is Sn less than t. What does this say? This says that nth event has occurred before or at t. If nth event has occurred before or at t, then number of events till t is either n or greater than n, because nth event has occurred before t. So let that before t be some s, then there could be some event which has occurred. The n plus one event could have occurred between s and t. So you can't say anything about nt equal to n, but you can say that nt is at least greater than n. It is at least n, because you know that n events have occurred till time t. So the other implication is also there. So both ways implication implies that both the events are equal. So nt greater than n is equal to the event that Sn is less than or equal to t. Okay. Yeah, so using this, we'll show that we'll find the distribution of Sn. Okay, so let me just again recap once again what we did last class. What we did was we modeled Poisson process counting process, and we tried to like come up with motivation of uh, why do I need counting process, and how do I get NT as a Poisson distribution uh, when NT is Poisson, and we came up with two definitions. This is definition one and definition two. From these, now in this class, what I'm trying to say is you need not always define a Poisson process using NT. You can also define a Poisson process using the interarrival times, excise. So you have set of excise such that xi belongs to xi is greater than 0 for all I. If you have a set of interarrival times, even then you have a Poisson process. And now what we are trying to do is we want to like if I give you excise, I want to go to numbers and number of events that have happened in T. And if I give you NT, then I want to come back to excise. So this shuffling is actually not easy. So to do that, what we can do is we show we generate a new term known as weighting distributions, SIs. So SIs and XS relations are very simple. So SI is summation of all the XS before it, and SI to NT is related using this uh, observation. So now you can interchange. So if you're comfortable solving problems in NT, then you use NT. If you're not, you want to change NTs to excise, then you can change NT to SM and then SN to excise, whichever way it works. So, but before that, we need to know all the distributions. So NT is distributed Poisson, XT is distributed exponentially, um, and we'll show that SN is distributed in Erlang distribution that I'll show. Okay. So now probability of NT greater than or equal to N equal to probability of Sn less than or equal to T. So since we know this both are equal, so NT greater than or equal to N is equal to probability of Sn less than or equal to T. This is basically summation J equal to N to infinity. This is for the Poisson process. Since we have Poisson process, J factor. So now this is the CDF of Sn. We want to, so this is the distribution of Sn T summation j equal to n to infinity e power minus lambda t power j by j factorial. Now we want to find the density function. The density function, you just differentiate the CDF with respect to t. So you have dfsnt by dt is equal to fsnt. This is the density function. So you're differentiating with respect to t. There are two terms which has t. So you apply the chain rule. So first we'll apply for this term. You get minus summation j equal to n to infinity lambda e power minus lambda t whole power j by j factorial. And then you apply it to the second term. You get j equal to n to infinity uh, e power minus lambda t. Okay, yeah, take one lambda out. Lambda t power j minus 1 by j factorial. So while taking the differentiation, a j comes out, j and j factorial gets cancelled. So I can directly write this as j minus 1 factorial. Okay, I hope the differentiation is clear. So next, summation j equal to n to infinity, lambda e power minus lambda t power j by j factorial plus. So what I'll do is I'll write this from j equal to n plus 1 to infinity. Lambda e power minus lambda t power j minus 1 by j minus 1 whole factorial plus the n term is remaining, lambda e power minus lambda t power n minus 1 by n minus 1 factorial. So as you can see, this goes from n plus 1. So when you put n plus 1 here, you get lambda t power n by n factorial. This term goes from n. So the first term goes from lambda t power n by n factorial. So these two summations are basically the same. You cancel it out. But before canceling it out, you need to check if they converge. And we actually they actually converge. So they converge. So you can cancel it out. Otherwise, you'll end up in all mm, cases like infinity minus infinity, which is not which doesn't make any sense. So these two terms converge because they are also part of a distribution, and they cancel out, and all you're remaining is with lambda e power minus lambda t power n minus 1 by n minus 1 factorial. Now this is the distribution of Erlang distribution. Okay, so if you don't know about Erlang distribution, I'll just give a quick recap. So the density of Erlang distribution is parameterized by two things, k and lambda. K is known as the space parameter, shape parameter, and lambda is known as rate parameter. So here you get lambda power k, x power k minus 1 e power minus lambda x by k minus 1 whole factor. This is the density function of Erlang distribution. So Erlang distributions you basically get when you add n Poisson distributions, n exponential distributions. Okay, so now I am writing this in the format which you'll recognize. So you get lambda power n. You have lambda here and lambda power n minus 1 here into e power minus lambda t into t power n minus 1 by n minus 1 factorial. So now you have a distribution t. Since you're finding the distribution of Sn is time. So Sn is Erlang. The dummy variable is t. The argument is t, and the parameters are n and lambda, where n tells you how many exponential variables you have added, because Sn is a sum of exponential variables. N tells you how many exponential variables you have added. Lambda is the rate at which the so it basically the lambda is the exponentials parameter. So how many exponential parameters and what is the parameter of exponential? Using these two terms, you can define the distribution of Sn, the Sn distribution. Okay. So there is one more way to um, obtain the density function of Sn. Maybe I'll leave it to you. I'll just say how you can obtain the density function of Sn. So probability of t less than Sn less than or equal to t plus dt. You can t plus delta t. You can write this as probability of nt equal to n minus 1 and one event in t comma t plus delta t plus order of delta t. So now why this plus order of delta t comes here is uh, when I say that t less than Sn less than equal t plus delta t, so till t n minus 1 events have occurred and one event has occurred in t comma t plus delta t. There is also a case where uh, Sn plus 1 can also occur before t plus delta t. But then what does it imply is the number of events in a small interval delta t is 2. So if two number of events have occurred in a small interval delta t, then according to Poisson distribution, it is of order delta t from the definition 2. Yeah. So two intervals, more than one interval occur, more than one event occurring in a small interval delta t, the probabilities in the order of delta t. So those all events go into this order of delta t. So only the event that remains is probability of nt equal to n minus 1 and one event in t to t plus 1. Even those events where Sn minus 1 occurs after t, but Sn occurs before t plus delta t. So there also what you have is you have two events occurring between t and t plus delta t. So even those go as higher order of delta t. And if you have many functions which are of order of delta t, if you add them up, you'll get a function which is also of the order delta t. I hope that is clear. Uh, Now you can use this and you can say that, okay, till t and t to t plus delta t, again, the intervals are non-overlapping. If the intervals are non-overlapping, that means that you can use the independent property. These two are independent. So you write them as a product. Nt is equal to n minus 1 into probability of one event occurring in interval delta t plus order of delta t. You write the Poisson distribution e power minus lambda t power n minus 1 by n minus 1 factorial into lambda dt plus order of delta t is delta t. And then you divide it by delta t and take delta t goes to 0. You get lambda e power minus lambda t n minus 1 by n minus 1 factorial, which is the same as this. So you can do any method you want. It's the same thing. So we're trying to find the distribution of um, waiting times. Uh, so now, yeah. So now what we have is, so we have Poisson process. So Poisson, okay, let me show last class. I think I've written this down. Okay. So, huh. So you had a, okay, so uh, l- uh, you have a random point process where you have events occurring at continuous time with constant mean rate lambda delta t. Each interval is independent. So when you want to mathematically characterize those models, what you get is you can look at an interval and count the number of events that have occurred. You will see that that is Poisson distribution. That becomes Poisson distribution, which we have seen in the fifth class. Or you can also see what is the time between the events, and you see that uh, it is exponential distribution. If you know that if you know that the random point process is a Poisson distribution. So these are two ways to look at a problem. You can either look at it through the Poisson distribution, the number of events that has occurred, or the time between those two events, which is the exponential distribution. So going from number to x might be difficult sometimes. So we also introduce something known as Sn, which is the summation of inter-arrival times. And we have seen that this is distributed with Erlang distribution. Okay. Next, before actually going into the conditional distribution of arrival times, yeah, I want to introduce order statistics. So, are you familiar with order statistics, or do you want to go through order statistics once?
Uh, no, I'm not familiar on that.
Okay, okay. So what I'll do is actually I'll go through order statistics once. Okay. So first, the basic intuition is so order statistics, it has something to do with ordering things. So order statistics is when you have a random sequence of events, but you don't want them in those events. You want to rearrange them in ascending order or in descending order. So order statistics is when you have sample values of random variables placed in ascending order or descending order. We'll talk about ascending order because as you can see, S1, S2, S3, S4, they all will have ascending order. It will go from small to big. It will never decrease. They're always increasing. So we will look at sample values placed in ascending order. So what do I mean by sample values placed in ascending order is, suppose I have n random variables, x1, x2, so on till xn. And these are IID. So they are independent and identical. So now what I call the order statistics is x1, x2, and so on till xn. So the bracketed term, this is the order statistics of the sample value. So once I generate a sample value, I can get the order statistics of it. So what does it mean is, suppose suppose n equal to 4, and I get the numbers. I do some random sampling between 0 and 100 or 0 and 10, uh, and I get the numbers 1, 4, 3, 6. So this is the sample path for the random variables that I've given, x1, x2, x3, x4. The ordered statistics are 1, 3, 4, and 6. These both will have different distributions. This distribution you know, but now I want to know the distribution of these events. So order statistics is, suppose I have x1 to xn random variables. Every sample path will have some numbers on it. If every time I replace it such that they're ordered from x1 to xn in ascending order, then I'll get a set of data. Those set of sample paths, uh, what is the distribution of those set of sample paths? Am I clear? Like, is this clear enough or?
Yeah, I got it now.
Okay. Uh, so let me, because I'm doing this, let me like continue with the order statistics only. So, okay. Okay, so x1, so suppose I have x1 to xn IID random variables. So x1 would be minimum of x1 to xn, right? X2 would be minimum of x1 to xn, but minus the term that you have, minus the least term. So it will be minimum of these two sets. X3 would be similarly minimum of x1 to xn minus the first two terms that you have, the first two minimum terms. This will go on, and xn would be max of all the terms. This is clear, right? So what this is telling is, um, this is the uh, least term, uh, mm, least value term. Okay, not value. This is the okay. How do you say it? Okay. This is the uh, term with the least value in the random process, the second least value, the third least value, the nth least value. So, hmm. So order statistics. Okay, so let me give an example of order statistics. So median is in order statistics, whereas mean is not in order statistics. So in median, what you do is you get a sample path, you arrange them in ascending order, and then you find the midpoint of that. So if your n is odd, then xn by 2 is your median. If it is not odd, then xn by 2 plus 1 plus xn by 2 by 2. That is your median. Okay, so just let me write it down. Median is an order statistic. Mean is not an order statistic. Is not. Okay. So uh, we'll try to actually find the distributions of these order statistics. Uh, why this will be useful is because uh, S size will have uniform distribution, but the uniform distribution is from actually the ordered statistics view, not the normal uniform distribution. Okay, so first what we'll do is are n random variables which are IID. Since they're IID, they have the same distribution. So I can write the distribution of all these are same. Let that be fx. The densities also would be same. So now let me find the, okay, these are for the uh, n random variables that we know. Now I want to find the distribution for x1, x2, and so on, xn. These are order statistics of the random variable that we have given here. But instead of finding the distribution first I'll find the distribution for nth order statistics. So this term, and this one for this term. So nth order statistic. So fnx is equal to probability of xn less than or equal to x. This is what you find when you like this is the cumulative distribution function. Now xn is the max of all those. So you have probability of max of x1 to xn. Now here x1 to xn, these are the sample path IDs. These are not the order statistics anymore, less than or equal to x. So what does this mean? Max of some set of events is less than some number. Means all those set of events should be less than x. Anyone, if anyone is greater than x, then max is not less than x. So what this means is x1 is less than x, x2 is less than x, and so on. Xn is less than x. Just to be clear that these are not the order statistics. Order statistics are the bracket that I've written. From the order statistics, I converted into the distribution which I know. So x1 is less than x, x2 is less than x, and this you get as fxx whole power n. And the density function for nth order statistics, you just differentiate this, you get fxn into fxx. This is the density function of them. Okay, I hope this is clear. This is the distribution for the nth order statistics. Um, Similarly, you can do for the first order statistics. First order statistics, okay, I'll tell. F1x equal to probability of x1 less than or equal to x, which is equal to probability of min x1 to xn less than or equal to x. But minimum less than or equal to x does not pose any extra conditions on the other terms. Other terms could be greater than x. So what you do is when you're uh, stuck with a min and less than or equal to, you just write the complement of it. And min is greater than x. Now, if min is greater than x, then all the terms should be greater than x. So, and again, because they are independent, you can write these are all complementary distributions. These are not distributions. So you have this is the distribution of the first order statistics, and the density function of the first order statistics is n1 minus fxx whole power n minus 1 fxx. You differentiate this with respect to x, you will get this. So this is the first order statistics. Now for kth order statistics, for any k between 0 and 1. for any k between 0 and 1. Okay, so this whole class, what we're trying to do is we are defining several random variables and trying to find the distributions of them. So distributions, densities. So once you're comfortable in all the distributions and densities and how to go from one distribution to another distribution to another, you'll see that in the next class we'll only see problems in Poisson distribution. So in the next class, when you see the problems in Poisson distribution, you'll be easily able to solve some problems which are easier in n. You'll solve it in x. You'll solve it in s. Whichever feels easy for you, you can solve it. Just changing from one to other is what matters. So yeah, fkx is equal to probability of xk less than or equal to x. Okay, so auto statistics, sorry, xk later. Now, what does it mean is probability that at least k of xi's are less than x. So xk, the order statistics xk less than x. So kth order statistic is less than x implies that kth order statistic should be less than x. It can also mean that k plus 1, if k plus 1th order statistic is also less than x, that implies that kth statistic is less than x. So from k, anything till n, if all are less than x, then probability of xk less than x also happens. So you sum up all the times when it goes from k to n and probability of exactly j of x of n xi's are less than or equal to x. So what it says is, suppose k plus 1, um, uh, so you have x1 to xn, right? Uh, now, what you need is for kth order statistic to be less than x, at least uh, k of the xi's are less than x, because the kth order statistic would be the k largest of them out of these random variables. So if just k are less than x, then you choose those k. But suppose if k plus 1 are less than x, then what you do is uh, you have to put that exactly k plus 1 are less than x. So uh, that even probability are calculated. Okay, I think I might have messed up this thing, but is it clear how I went from here to here?
Yes, sir.
Hello, I didn't get. Do you want me to explain again?
Yes, sir.
Okay, so here to here, what happened is, so uh, kth order statistic is less than x. So this is the kth order statistics. So kth order statistics is less than x means if I'm given n terms, at least k terms should be less than x. Now, what are those k terms? I don't know. It could be any of the k terms. So, okay, let me split this up first. Okay, so first what I'm writing is, so kth order statistic less than x means probability k terms in original sequence, the x1 to not the order statistics, xn are less than x. K terms in those are less than x. If k terms in those are less than x, then the kth order statistic would be less than x, right? That makes sense. Okay. Uh, yeah. K terms are less than x. Now I have to choose which k terms are less than x in that. So which k terms in these are less than x. That is why this is exactly j. Now, suppose probability k plus 1 terms in x1 to xn is less than x. Even if k plus 1 terms in x1 to xn is less than x, even then the kth order statistic will be less than x. So what I'm trying to say is, okay, so suppose I have n equal to 5. Okay, 5 random numbers, 5, 4, 6, 8, 9. Okay, and my x is say mm, mm, s- uh, 8. Okay, so now if now I'm looking at x2. So if I rearrange this, what I'll get is 4, 5, 6, 8, 9. Okay, I've given it in very ordered manner everyone. Okay, so x2 is 5, and so my I'm looking at 8. So I want that x2 is less than 8. For x2 to be less than 8, at least two of the numbers should be less than 8. Because if only one number is less than 8, then x2 can never be less than 8. Okay, maybe I've given a high x here. Okay, let me take x as 3. Now for x2 to be less than 3, I need at least two numbers to be less than 3. But here no number is less than 3. So x2 can never be less than 3. But if x is 6, I need at least two numbers so that x2 is less than 6. I need at least two numbers to be less than 6. And here there are two numbers less than 6. So it passes. But then if x2 is 8, if x is 8 and x2 is less than 8, I need at least two numbers to be less than 8. Here, three numbers are less than 8, but it doesn't matter. My x2 is anyhow less than 8. Does this make sense? Why I'm splitting out the events? So the first is where 2 are less than x. The second is where 3 are less than x. The 4 are less than x, so on. So to find the distribution of kth order statistics, in the original random variables, you have to choose k terms in the first, or k plus 1 terms, or k plus 2 terms till n terms. If all n terms are less than x, then you're done. Then obviously the kth order statistic also will be less than. Is this clear, or am I still confused?
Yeah, it's clear. Sure.
Okay, okay, okay. So summation j equal to k to n, probability exactly j of n xi's. These xi's are not from uh, the order statistics. They're from the normal, the random variables that are being given are less than or equal to x. Now what you do is you choose out of those n. So summation j equal to k to n. Choosing j out of them, it could be anyone, and the ones that you have chosen should actually be less than x. So the probability that they're less than x is fxx. N of them should be less than, oh, j of them sorry, j of them should be less than x, and the remaining could be greater. I don't, it's like n minus. So here you have covered all the cases. So this is the distribution of kth order statistics, and the density of the kth order statistics. You differentiate this with respect to x, you will get, again you have to apply the chain rule. You'll get one term for this, one term for this. In a similar way, we did the Poisson distribution. Here we cancel out the terms and we got the net distribution. Similarly, if you write this out totally, you'll get two terms. One term would start from one and one term would end from another. So all those summations would cancel out, and what will remain is nck into k fxx whole power k minus 1 minus fxx whole power n minus k efxx. You can try it out later. If you have any doubt, you can ask me in the next class. I'll do this. Uh, okay. So next, what I want is actually I want the joint distributions. So till now, what we have learned is order statistics, the distributions of individual each one of them. The nth order statistics distribution, the kth order statistics, the first order statistics distribution. Now we'll learn is how to calculate the joint distributions. So joint distributions of x1 and xn. So f of x1 comma xn. The arguments are x comma y. This is basically what you write as x1 less than or equal to x, xn less than or equal to y. Um, okay, this I can write as probability of xn less than or equal to y minus probability of x1 greater than x and xn less than or equal to y. Hmm. So now I want to evaluate this term. So this term, there will be two cases. One case is x greater than or equal to y, and one case is x less than y. So suppose x is greater than or equal to y. So suppose x is greater than or equal to y. Then could you tell me what would the probability of this event be? So you have x here and you have y here. What you're saying is x1 is greater than x. So x1 is somewhere here. And you're saying xn is less than y. You're saying xn is this is order statistics. So the probability of this event would be the probability of this event would be 0 because x1 can never be greater than xn in the order statistics. I've not yet changed it to x's. I'm just in the uh, order statistics domain. Okay. The second part is if x is less than y. If x is less than y, then what I'm saying is x is here and y is here. And I'm saying that x1 is greater than x and xn is less than y. So what does this mean is all the others are also in between uh, x and y because any one of them can't go beyond y and any one of them can't go less than x1. If it goes less than x1, then x1 is not x1. The one which goes less than x1 is the x1. Yeah, so then this probability boils down to probability of mm, x bit x1. Okay, so what does this mean is all the xi's are between x and y. So if the all the random variables in the order statistics are between x and y, the original one also will have all of them between x and y. So I can convert it into x and y. So x less than x2 less than y, so on, x less than xn less than y. And then using independent and identical distribution, I can write this as fy minus fx whole power n. And the distribution for this is fny. Fny was fxy whole power n. We calculated the nth order distribution there. So the joint distribution for 1 and n is the joint distribution for 1 and n is fy power n minus fy minus fx whole power n. Okay, now to calculate the density function, what you do is you differentiate this with respect to x and y, partial differentiate 2x 2y. Um, what you'll get is n into n minus 1 into fy minus fx n minus 2 into fx fy. You can try this out, and if you don't get it you can ask me. But now what happens is as you keep on increasing the number of order statistics here. So you'll see that this term will keep on increasing. So if you find the joint distribution of x1, x2, x3, one more term would come out here, and here one more term would decrease. X1, x2, x3, x4, one more term. So this term will basically be the factorial term. So what is the distribution of x1, x2, and so on to xn? X1, comma x2, comma so on till xn is basically n factorial fx1, fx2, fx3, so on till fxn. This is the joint distribution of the order statistics. So why does this n factorial come into play? Is the intuitive reason behind this is there are n factorial way of arranging the original terms. So the density gets multiplied by an n factorial term. I hope that is clear. So okay, this whole ordered statistics was um, off topic. So what we did. So I hope now everything is clear with ordered statistics. Okay. So now. Uh, okay. Yeah, I'm running short on time. Uh, okay, then I'll do the proof. The conditioning on distribution and arrival times. Okay. Okay, I'll just give the theorem on what I'm trying to do in the next class. I have two the I have one I have one theorem to do. That theorem proof, I think now if I start, it will take up time. So I'll just give you the uh, theorem statement and give some intuition behind it, and I'll stop the class. Next class, I'll do the theorem, and then we'll go into problems for Poisson process. We'll do different types of problems from queuing theory, from normal, like any process, any real life instance which has been modeled as a Poisson process. How do you solve some from those? We'll do in that next class. Okay, so theorem that I wanted to say was uh, the theorem was given nt equal to n, you have n arrival times, right? S1, S2, and so on, Sn. The joint distribution of these random variables is the same as the order statistics corresponding to n independent random variable uniformly distributed on 0, t. Okay, so what does this mean is that condition on the number of, so if I know that there are in time t n number of events have occurred, then the distribution of S1 to Sn is the ordered statistic distribution of uniform distribution uh, uh, n independent uniform distributed random variables on 0 to t. Hope that is clear. So what I'm trying to prove is, if I know that already n events have occurred in some time interval, then the joint distribution of S1, S2, Sn is the ordered statistic distribution of n independent uniformly distributed random variable on 0 to t. This theorem I'll prove in the next class. And this theorem will help us to show also splitting of Poisson process and combining of Poisson process. And after that, we are basically done with Poisson process. We'll do some sums on Poisson process. Yeah, we'll do sums on Poisson process. Yes. And oh yeah, the next class will do sums on Poisson process. So what I've taught now is homogeneous Poisson process. Next I'll come into non-homogeneous Poisson process and motivate why non-homogeneous Poisson process is necessary, and then we'll do some sums. Yeah, I'll stop the recording maybe, and then if you have some